So, good morning, everybody. There's some noise in the microphone, and I don't know whether it's from me or you or something else. I hope it's not going to be too distracting. All right, where are we? We discussed last time the transverse dielectric function and converted both the longitudinal and the transverse dielectric function into dispersion relations. We saw several examples. For example, we looked at the large frequency limit of the propagation condition for transverse electromagnetic waves. We looked equally at the large frequency limit of the propagation condition for longitudinal waves. And I showed you at the end the ion acoustic wave, which was one indication of what happens if we take into account that the plasma is typically a mixture of at least two species, the electrons and the ions. And of course, there should be a lot more species just because the ions are of different type. All right, this was one indication of how we can study the propagation of electromagnetic waves in plasmas and at the same time study plasma waves. I told you last time we analyzed the formation of waves in the electron distribution, and by our assumption of linear response, this is at the same time the study of the propagation of electromagnetic waves through the plasma. And the scheme that we applied was, first of all, that we needed to satisfy Maxwell's equations, of course, and that we assumed to have linear response in the medium. All right, this theme will, of course, recur. Do you have questions up to this point? If that is not the case, then I would like to continue with magnetohydrodynamics. So we are now at section 4.5 in this book here, if you want to have a look. And as I envisaged last time, the main logic will be, first of all, to see how we need to augment the hydrodynamical equations if there is a magnetic field present, how we need to study or which equation controls the back reaction of the medium, the plasma, on the magnetic field. And then we will have to move on with waves in plasmas, magnetized plasmas, and so on and so forth. All right. But let us first briefly have a look at why magnetic fields can be sustained in a plasma in the first place. Because remember, what we are looking at is a macroscopically neutral plasma. So on a macroscopic or mesoscopic average, there are no charges. So are there no currents? Suppose the electrons and the ions would flow in the same manner, right? Then we would not have any currents. If we have no currents, we have no magnetic fields. If we have no charges, we have no electric fields. We could create magnetic fields by a time change in an electric field, but in a macroscopically neutral plasma, we can hardly sustain a macroscopic electric field. So how can there be magnetic fields in plasmas in the first place? They can be there because electrons and ions may have a drift velocity with respect to each other. And if that is the case, you can have macroscopically neutral conditions and at the same time have relatively strong currents. Right? If the electrons and the ions move in an appropriate way against each other, if there is a drift velocity between the two, then there can be a magnetic field in the plasma, even though the plasma is macroscopically neutral. All right. And now the way how we are going to look at the magnetohydrodynamical equation is going to be the following. We first transform into the rest frame of the plasma and analyze the situation under the condition that free charges are rare, but currents are strong. And because free charges are rare, there is hardly any electric field, and therefore we also neglect the displacement current, right? The E dot or D dot term in Maxwell's equations. Yes?
If you say that you have relative velocity of ions and electrons, what's the rest frame of plasma?
The rest frame of the ions, because they move much more slowly. Yeah, we could also take the mass averaged rest frame, but this would amount to the same thing. Okay, good. So these are going to be the conditions under which we are going to analyze that. I thought this is nice, so we leave that here. So if I mark quantities in the rest frame of the plasma with a prime, the conditions we are looking at are the following. Rho prime, that's the free charge density. I need to compare this in some way with the current density, so I need to multiply this with the velocity. And I'm going to use the speed of light in order to have the zero component of the four-dimensional, the covariant charge current density, J mu, right? All right, so the absolute value of this is supposed to be much smaller than the absolute value of the current density in the plasma rest frame. In line with that, we are going to assume that the electric field is much smaller than the magnetic field. What we therefore can also assume is that the displacement current is much smaller than the charge current. And what we also want to assume is that the plasma is slow. Right? Slow in relativistic terms. So these are the conditions that we want to apply. Now, in order to leave the rest frame of the plasma and to go, for example, to the observer's frame or some kind of laboratory frame, we need to apply a Lorentz transform. And I'm going to sketch the Lorentz transform in 2 dimensions, just to make the following statements plausible. I'm going to represent the Lorentz transform by a 2-dimensional matrix. And first of all, that matrix would look like this if I had a relativistic flow. But now, under our condition of a non-relativistic flow, I can approximate gamma by 1. And then I can represent the Lorentz transform in this way. And of course, you could replace beta by minus beta if you just reversed the transformation direction. But this is not important for our case. All right, now, if I reduce my current density vector by 1 component, or to 1 component, J prime, I would transform like that here. And so I would have to multiply this matrix here with this 2-dimensional vector. And now I'm targeting the J prime component. And I can write J prime is beta C rho plus J. All right, if I reverse the Lorentz transform, the equation would look like this, right? And, with a prime on the rho. So this means that if the charge density in the rest frame is very small, C rho prime is much less than J prime, then this term here, which has a further factor of beta, which is much smaller than 1, is entirely negligible in this transformation. So the first conclusion we draw from there is that J approximately J prime. Isn't that nice? Now, also, if you look at the charge density, right, I say C rho prime is C rho plus beta J, or with the inverse transformation, then you see if C rho prime is small and beta is small, then C rho will also be small. And so if the charge density in the rest frame is small, then the charge density in the laboratory frame is also going to be small. And we can carry the first assumption here to the laboratory frame as well. All right. We are going to use that. And we are going to use C rho absolute much less than 1 as well as we move on. Okay, but if C rho in the laboratory frame is also small, then the source for any electric field in the laboratory frame is also very small. So then we are going to assume in the laboratory frame as well that the electric field is going to be much smaller than the magnetic field. So we are going to carry our second assumption also into the laboratory frame, and likewise with our third assumption here. Right? We just see that any source for the electric field is going to be small, and therefore we feel safe to assume that if magnetic fields dominate in the rest frame of the plasma, then they will also dominate in the laboratory frame. And this, of course, could be different if we had relativistic motion. Right? In a relativistic magnetized plasma, the situation would look different, then we would have to apply different means. Nonetheless, now we need to see how we relate the electric field E prime to the electric field E and the magnetic field B in the laboratory frame. The reason is that if the plasma has a finite conductivity, and of course we'll have that, right, because it's full of charges, of free charges, then we will have, or we can assume, a linear relation between the current density J prime and the electric field E prime in the rest frame of the plasma. But then, if we cannot neglect J prime, we cannot neglect E prime either. And it will have a small contribution, okay, but it will be there. So if I replace E prime here by Ohm's law from there, this is going to be J prime divided by sigma. But J prime is approximately J. So this will be J over sigma. So careful, right? Even though we say that the magnetic field dominates, we cannot neglect the electric field altogether. But we are going to represent the electric field in terms of the current density by means of the conductivity sigma. If the conductivity is infinitely large, which you can often assume in a plasma, then of course we need to be careful with a relation like that. But for now we are going to assume that sigma is finite, large but finite. All right, so what is our set of equations now? we start with this one here and say E plus beta cross B equals J over sigma. Notice that this combines, this has nothing to do with Maxwell's equations, right? This is just a Lorentz transform combined with the assumption of linear response between the current density J and the electric field E. But now we have to use, of course, Maxwell's equations. The only one that we ignore is going to be diff E equals 4 pi rho, because we don't care about the electric field. All right, so we have diff B equals 0. We have C times the curl of B, C times the curl of E plus B dot equals 0. And what else do we have? We have C times the curl of B. Now, we should continue with minus E dot, right, in order to complete the equation, but we are ignoring the displacement current. So the next thing is the equal sign, and then we have 4 pi J. So these are the three Maxwell's equations that we take into account, plus we have the Lorentz transform of the electric field. All right, now I'm going to use this equation here because I want to have a dynamical equation for the magnetic field. That's the point. So from this equation here, I get B dot equals minus C, the curl of E. But I have an expression for E above. Right, that's from the Lorentz transform and the linear response. So I get minus C. Now, the curl of something lengthy, right? This is going to be J divided by sigma minus beta cross B. I'm just inserting the result of the back transform of E into that. Minus C over sigma times the curl of J. In order to get that, I'm reading this equation backwards. And I get minus C over sigma. Now the curl of what? Of J, that's C over 4 pi. Now, curl of B. That's a very interesting term. We'll see about that. Next thing. So we are done with this one. But again, of course, we have assumed that the conductivity sigma is spatially constant. It doesn't need to be. Suppose you are at the boundary of a plasma distribution where the degree of ionization in the plasma gradually goes down, right? And the plasma gradually turns into a neutral gas. Then, of course, the conductivity will depend on space, but I'm ignoring that for now, and I'm pulling the sigma out here. What else? We get a plus C times beta, that's V. So we have plus the curl of V cross B. Okay. So now we have a dynamical equation for the magnetic field. Let me pull terms together. This is minus C squared divided by 4 pi sigma. Then we have the curl of B. And this is the gradient of the divergence of B minus the Laplacian applied to B. Right, that's the double curl. And the divergence of B, of course, is 0. And then we have the curl of V cross B. Now we can ignore this one once and for all. And we arrive at the beautiful equation dB dt equals c squared over 4 pi sigma nabla square b plus the curl of V cross B. This is already a most important result, right? That's the so-called induction equation for the magnetic field. What does it tell you? First of all, this term here, curl of V cross B, that tells you how the flow of the plasma acts back on the magnetic field. So the plasma will move around, it will carry the magnetic field around. We will have to see why it does, right? And there's an additional extremely interesting term here that goes with the Laplacian of B. So here, suppose you could neglect this one, right? Slowly moving plasma. And suppose you had this only, then what would that be? Right? What type of equation is that? You have a single time derivative, and you have a double spatial derivative. Schrödinger's equation, right? This is a diffusion equation, right? You equate a single time derivative to a double spatial derivative. That's a diffusion equation. We are going to see about that. So if the conductivity is finite, there will be magnetic field diffusion. If the conductivity is infinite, the diffusion is gone. We need to return to that because you have seen an equation like that already in hydrodynamics, viscous hydrodynamics, and I'm going to compare that to that. But this is the magnetic induction equation. All right, it's beautiful. It tells you how the magnetic field is going to change under diffusion and flows. It does not tell you how magnetic fields originate. And this is really bad, right? Because the equation is homogeneous in B. So if you start with B equals 0, it will never create a B. If you have no B, you get no B, right? That's like capitalism. So this equation has it tells you how the magnetic field responds to the plasma flow. It does not tell you how magnetic fields originate. So we need to return this later. And it tells you already that if you want to create a magnetic field to begin with, a single component plasma is not going to be good enough, right? Because in a single component plasma we get an equation like that. So we will need at least a two-component plasma, and we are going to see about that. All right, lovely. So we know how the fluid flow acts back on the magnetic field. Now we need to see how the presence of the magnetic field changes the fluid flow. Now, first of all, the continuity equation, mass conservation, is not going to be changed at all. The magnetic field does not occur in this equation, and it will not occur because it does not interfere with the conservation of mass in the fluid flow. So this is going to remain. But now, if I write Euler's equation in this way here, rho times the total acceleration, dv dt, equals minus gradient p minus gradient phi. Right? We said, okay, the acceleration, that's, well, mass density times acceleration, so that's a force density. This is compensated by the pressure gradient and the gradient of the gravitational potential. this will have to be augmented by magnetic force density. Right, so we have to insert this here, or we have to do this in a systematic way. But let me first insert this right away. So we need a magnetic force density. Okay, we said that we lightheartedly ignore electric fields. Right, so the Lorentz force will have exactly one component, and this will be something like this. Now, if I multiply this with the electric charge of an electron, I get the force on a single electron. And if I multiply with the number density of electrons, I will get the force density due to magnetic fields on the electrons. Right, that is the magnetic force density that I've been looking for, ignoring any electric field contributions. Okay. But now, if I look at the charge current density of the electrons, right, this is going to be minus NE times V. Okay, so the magnetic force density is just J over C cross B. All right. But now I need to replace the J also by the magnetic field. Right? Now I can use, can you see this on the board up here? Now I can use one of Maxwell's equations to directly relate the current density to the curl of the magnetic field. So I can write magnetic force density. This is 1 over C. Now the expression for the current density, so that's C over 4 pi curl B. Vector product times B. So that is the magnetic force density. C cancels out. I get 1 over 4 pi curl P times B. Okay, now this doesn't tell a lot, right? But let me remind you of an expression that we had made use of in hydrodynamics, namely that if I take a vector field A and I take the vector product of that times the curl of itself, right? A times curl of A, then this is going to be the gradient of A squared over 2 minus A times the gradient times A. You remember, do you? We used that when we discussed the circulation. Do you believe this, or do you want to see it? No. Then believe it, okay? So, now we use that to express the magnetic force density in the Euler equation. So this means that we can now write the Euler equation. I'm now going to write it in full so this is the total time derivative of the velocity Then on the right-hand side, I have minus gradient P. Then I have minus gradient phi, if there is a gravitational potential. And then I have two terms from here. Now this is the negative. This expression here is the negative of that, right? Because in order to arrive there, I need to replace the b and the curl b factors. So I'm going to start with minus 4 pi minus b gradient b. So that's plus 1 over 4 pi b gradient b. That's the first term we are getting. This is very illustrative, as you will see. And then we have minus gradient b squared over 2. So 1 over 4 pi gradient b squared over 2. Okay, this is Euler's equation now in presence of a magnetic field. So this tells you how the magnetic field acts back on the flow of the fluid, of the plasma. So now we have two equations. One is how the flow changes the magnetic field. Then we have an equation that tells you how the magnetic field changes the flow. What does it tell you? Well, first of all, you can combine two of these gradients to see that we can write there's a gradient of P plus b squared over 8 pi. B squared over 8 pi is the magnetic pressure. Right? This is the degree to which the magnetic field resists being squeezed. Then we have the gravitational potential as usual, and 1 over 4 pi b times gradient times b. Now what is this? What is this here? B times gradient applied to b. This is the directional derivative in b direction applied to b itself. So this tells you by how much the magnetic field changes along its own direction. In other words, this term tells you how curved the magnetic field lines are. So there's a force that comes from the curvature of the magnetic field. And if you bend magnetic fields strongly, they will try and resist. Okay? So you see two very intuitive additions to Euler's equation. First of all, there's a magnetic field density which resists being compressed. And there's a tension in the magnetic field that tells you that magnetic field lines want to be as straight as possible. And if they are not, they will lead to an acceleration of the fluid. All right? Very intuitive. So this is Euler's equation. Euler with B, right? And of course, you can imagine what happens if you now look not at Euler's equation, but at the Navier-Stokes equation, which replaces Euler's equation in place of in case of viscous fluid. So then you would have two more terms, right? The term that is decorated with the eta viscosity and the one that's decorated with the zeta viscosity, and they will also go into that. So Navier-Stokes equations with magnetic field, beautiful. All right, so this is magnetic pressure, and this is magnetic tension here. Okay. So usually we would have this equation here. So in fact, these are three equations. Then we would have the continuity equation, and we have the induction equation. Further three equations. For how many variables? Magnetic field, 3 components. Velocity, 3 components. Density, 1 component. Pressure, 1 component. So we have 7 equations here. We have 8 components to solve for. But this is exactly the same as the situation we have in hydrodynamics. Right? So if you add now an equation that tells you how the pressure responds to the density, then the system is closed and we can move along. So this means that once we have the induction equation, the continuity equation, and Euler's equation with a magnetic field here, plus an equation that tells us what the pressure of the gas is, then we have a closed set of equations and we can move on. In other cases, we have to look at the energy equation as well. And what I'm going to show you now is not a full derivation, because that will cover 2 boards easily. I just want to tell you what happens. Right, so the energy density that was rho times v squared over 2 plus epsilon, right, where rho times v squared over 2 was the kinetic energy density and epsilon was the heat, right, the internal energy. That is going to change to rho v squared over 2 plus epsilon plus the energy density of the magnetic field, p squared over 8 pi. All right. Then, of course, we will also have to replace or augment the energy current density. Now, what was that? We had rho times v squared over 2 plus h times v, right? This was the energy current density in absence of the magnetic field. And again, that contains the kinetic energy current density, rho v squared over 2 times v. And instead of the internal energy epsilon, and internal energy density epsilon contains the enthalpy density here, right, to take into account that the energy current will have to do pressure volume work. And therefore, the internal energy is replaced by the enthalpy. All right, what's going to happen to that? Not much, except that we will have to add here the energy current density in the magnetic field, and that's the Poynting vector. Now let us briefly have a look at the Poynting vector. Poynting vector. C over 4 pi times E cross B. What was E again? We had an expression for the electric field in the laboratory frame. Right? Sorry. This time it was me. All right. So there is no choice. We will have to insert. We have to insert this expression here for the electric field in the Poynting vector. All right. So this is J divided by sigma minus beta cross B. And with that, we have to take a vector product with B. Now, of course, we have to replace J again, right, from this Maxwell equation here. So it's getting horrendously complicated here. So C over 4 pi, 1 over sigma, and J is C over 4 pi curl B. This is this term here. And then we have beta cross B cross B. All right, now you can assemble things, of course. So this means that the energy current density in the magnetic field will have a component that goes like 1 over sigma, so that goes away if the plasma is ideally conducting, right? If sigma goes to infinity. And then the term looks very much like the force density term that we already put into Euler's equation. Right? That has a contribution that contains the gradient of the magnetic pressure. In other words, the magnetic pressure is going to drive part of the energy current in the magnetic field. That will contain a part that is proportional to the curvature of the magnetic field lines, the B times gradient applied to B term. So this means that also the tension in the magnetic field is going to drive energy through the plasma. And then we have this term here, right, which as a double vector product, you can apply the Grassmann identity, and that tells you how the magnetic field energy flows with the plasma velocity. If you like, write it out. I don't. Now, imagine these were the contributions to the energy conservation equation in case of an ideal fluid. We had additional terms, right? We had gradient T terms with a heat conductivity. We had friction terms with a second derivative of the with a tensor, the second rank tensor of first order derivatives of the velocity field, and so on and so forth. Right? So if you want to set up the complete set of equations, right, you add viscosity terms here, you add friction and heat conductivity terms to the heat conduction equation, and then you have a full set of equations. And then, of course, you need a computer because you can't handle them anymore. All right. Since the board, okay. What I wanted to tell you is, first of all, what do we learn in the first place about the influence of the plasma flow on the magnetic field? We saw the induction equation here, and remember what the conditions were under which we derived it, namely that we can neglect charge densities compared to current densities, that we can neglect the displacement current E dot compared to the charge current, and that the plasma is slow. These were the conditions that we used to derive the magnetic induction equation. It has two very interesting terms. We'll deal with that. And then we looked at the back reaction of the magnetic field on the plasma flow in the ideal case, right? In the case of absent viscosity, absent heat conduction, absent friction in the plasma. Then we have the unchanged continuity equation. We saw how we have to augment the Euler equation, namely by a term that tells you that magnetic fields don't want to be compressed or squeezed, and a term that tells you that magnetic fields do not want to be bent. Very intuitive. And we saw how we have to augment the energy conservation equation and then stopped, right? Because it just becomes too tedious to write all these terms down. But you see the principle, right? Okay, so now is the right moment for the break. Let us break for 5 minutes and then continue a few minutes after 10 o'clock. Ready to go? Before we move on, I need to tell you an anecdote. One of my first PhD students was working on magnetohydrodynamics in galaxy clusters. So then he had his PhD exam. That was together with Harald Lesch in Munich. And Harald wanted to be friendly and said, look, could you write down these equations in the first place? And the PhD student said, no. And Harald was looking at him and said, excuse me. And the PhD student said, no, I'm so nervous, I'm going to make mistakes. And before I make any mistakes, I'm not going to write down these equations. All right. It didn't hurt him a lot. But okay. Let me remind of another equation that you had already seen. I'm starting with this one. So let me, it's part of the Navier-Stokes equation, right? And let me ignore the term with divergence of B, just assuming for the moment and for simplicity that we had an incompressible flow. Why not, right? Now, again, I'm going to make use of this of this equation. You have seen this before, right? I just want to remind you of that. In order to replace this term here, say, so this one, I'm going to replace by that one. So that's going to be nabla v squared over 2 minus v cross curl v. All right. Maybe you remember, maybe you don't, but this is the quantity we called omega before, the vorticity of the flow, and the curl of the velocity field. All right, now I'm sorry, there's a row missing here. If I write the row here, I need to write it here as well. Okay, now let me divide by row, then take the curl of another curl of this equation, and assume that we have a barotropic flow. Do you remember what a barotropic flow is? One that has aligned gradients of pressure and density, right? Where pressure gradient vectorially multiplied with density gradient is 0. Okay, in that case, first of all, I can write d omega dt, right? Again, I divide by rho, I take the curl. Divide by rho, I take the curl, I'm getting d omega dt. I take the curl of this gradient, then it's gone. Then I take minus the curl of v cross omega. That's this term. Then here I take the curl of minus the pressure gradient divided by density. But if I make my barotropic assumption, then that's going to be 0 as well, because then I'm taking a gradient, I'm taking the curl of a gradient. Here the density is gone, I'm taking the curl of a gradient, it's gone. So what remains is just eta times nabla square omega. Does that look familiar now? Induction. dB dt is c squared over 4 pi sigma Laplace square b plus a curl of 3 cross b. Vorticity d omega dt equals, well, that's eta over rho. This is often called dynamic viscosity nu. Nu times Laplace square omega plus curl of v times omega. They obey exactly the same equations. Okay? They both have the same structure, obviously. This is called the advection term. Advehi, Latin, to drag with. Right? So that's a term that shows how the flow of either the fluid or the plasma are dragging either the vorticity or the magnetic field around. It's the advection term. And this is the diffusion term. So this is a balance between, or both equations describe a balance between advection and diffusion. Okay, and in order to justify that we call this a diffusion term, let me briefly have a look at a field A, vector field A, that satisfies an equation like that. I told you that's a diffusion equation, but let me justify that. Yeah, how do you go about this? I mean, there's a partial differential equation, and the usual way how to proceed is separation ansatz. Right? So you would write A is f of t times g of x. And here you would say this is g times f dot. And on the right-hand side, you would say this is cf times Laplace square g. And then you do the usual thing, right? You separate, and you see f dot over f is c times Laplace square g over g. Now you have the usual situation that you have an equation purely of time on the left-hand side and purely of x on the right-hand side, and they can only be satisfied if they both are the same constant. So let us call the constant minus k squared. Why not? And then we have this condition in order to solve this equation. And then you see, first of all, from the left bit of this equation, f dot over f is a constant, so this means that f has to satisfy an exponential behavior. Right? Whenever the change of a function is proportional to itself, the result must be an exponential behavior, and you see f must be some f0 times e to the power of minus k squared t. If you take the time derivative, you just get a factor of minus k squared down, and then this is satisfied. And if you look at the right bit of this equation, well, this gives you the same kind of oscillator equation in the function g that is now depending on the vector x. If it depended on x only, right, then you would have an equation like g double prime divided by g plus c, k squared over c equals 0, or g double prime plus k squared over c times g equals 0. Right, so you would have an oscillator equation with a negative frequency squared. No, sorry. With a positive frequency squared, right? And then you would get the usual oscillator solutions. But here you see the amplitude of the field is going to decay exponentially in time. And the decay, or the argument of the exponential, is linear in time. And this characterizes a diffusion process. And for the rest, we will ask you to carry this out in a problem. Right? Okay. So you see here that you get an exponential decay of the amplitude. Now let us apply this to both these cases here. Here you would have, if I just take the amplitude b of the, if I just take b for the amplitude of the magnetic field, this would be c squared divided by 4 pi sigma. And suppose I would insert for b a plane wave, right? Then the nabla square would just give you a minus k squared times b. Right, so to set an example, right, I just decompose the B field into plane waves in space, and then the Laplacian just returns minus k squared b. Now you see I'm getting exponential behavior because b dot is proportional to b, and this means that b is going to be proportional to e to the minus k squared c squared divided by 4 pi sigma times t. So this allows you to extract a diffusion timescale. Right? If you write this as exponential of minus t divided by a diffusion timescale, you can directly read off what the diffusion timescale for the magnetic field is. So in this case, this would be 4 pi sigma divided by c squared k squared. All right. Now you could convert the k to a wavelength, if you like, which would tell you how quickly magnetic field structures of a certain wavelength would decay diffusively. But here you see that if the conductivity of the plasma is infinite, and the galaxy, for example, our Milky Way galaxy, has the conductivity of copper, for example, it's pretty good. So suppose sigma is infinite, then the diffusion timescale is also infinite and nothing diffuses. And this is what people mean often in the astrophysical literature if they say that then the magnetic field is frozen into the plasma, which I think is a classical misnomer, right? Because it's not frozen, because otherwise you would not have a plasma. But then the plasma cannot move with respect to the magnetic field cannot move within the plasma. Right? Then there is no diffusion, there is no relative motion of the magnetic field with respect to the plasma, and the advection term completely dominates. Why is that so? If you had infinite conductivity, then any very small change of the plasma distribution with respect to the magnetic field would induce an electric field, right? Because then the plasma would see a time-dependent magnetic field. This would induce an electric field that would immediately reinstall the plasma distribution as before. Okay? All right. Now, if you return to the other equation, the evolution equation for the vorticity, you see exactly the same effect due to viscosity. Right? So viscosity will lead to a diffusion of vorticity. In other words, eddies in the fluid are going to diffuse, right? They are going to spread out and disappear if the fluid is viscous. And again, you can derive a diffusion timescale just from here. Right? It would be 1 over k squared nu, and nu is the dynamic viscosity here. So in other words, if the viscosity is very large, then the diffusion timescale is very short. Right? Let me oppose this here. So then you see where you have c squared over 4 pi sigma. In the induction case, you would just have nu in the viscosity case, and so, or vorticity case, and so c squared over 4 pi sigma would be replaced by nu, so this would be 1 over k squared nu. So if the viscosity is large, the diffusion timescale is short, and eddies are going to dissipate very quickly. And if viscosity is very small, and so on and so forth. Okay, isn't this beautiful, right? The magnetic field behaves exactly like vorticity in a viscous fluid. Right? And if you have infinite conductivity, then there is no diffusion, and the advection term dominates. And if there is a lot of, if there is non-ideal conductivity, right, then you will have a balance between these two terms. Now let us have a look at the balance between the advection and the diffusion terms. I should write it down here, but I'm going to need the space. So we take the ratio of advection and diffusion, and we approximate all the gradients that appear there, or all the spatial derivatives, by taking 1 over L. That sounds crude, but it isn't. Suppose you would insert plane wave solutions, right? Then any of the gradients would just return a k, which is 1 over L. Well, it's not so bad. I know it looks ugly, but okay. So we would have V times B divided by L. That would be the advection term, okay? Taken from the induction equation. Here, V times B divided by L. This is an order of magnitude estimate that we are going to make. And we divide this by the magnitude of the diffusion term, so that's L squared B, and then the inverse of the prefactor here. So 4 pi sigma over c squared times L squared divided by B. That's the ratio of these two. Okay, one of the L cancels, one of the B cancels. We have 4 pi sigma divided by c squared times VL. Typical plasma velocity, typical length scale of the distribution, and conductivity. All right, now let us do the same thing for the vorticity equation. Again, we have V times omega divided by L. That's the order of magnitude of the advection term in the vorticity equation. And then we just have nu times, or we need to divide by nu times omega divided by L squared. So that's L squared divided by nu omega. Okay, again, omega cancels out, one of the L's cancels out. What remains is VL divided by nu. These numbers, and they need to be dimensionless, right? Because we are now comparing two terms that are added on the right-hand side of the same equation. These must be dimensionless numbers. They are called Reynolds numbers. This one is the magnetic Reynolds number, and this is the viscous Reynolds number here. And what does it tell you? Or what do both of them tell you? They tell you whether advection wins or whether vorticity diffusion or magnetic field diffusion wins. So if you had situations with very high Reynolds numbers, you would either have the case of an ideally conducting plasma or the case of an ideal fluid. And if you had very low Reynolds numbers, you need to be aware that diffusion terms dominate and magnetic fields go away and vorticity goes away. Okay? Very important concept, right? Very often you hear people speak about this flow has a Reynolds number of something, and then you're supposed to know what that means. And very often people speak of a numerical Reynolds number or numerical viscosity. That's very interesting because even if you set a hydrodynamical problem on a computer and you think the computer solves the ideal hydrodynamical equations, it doesn't, right? Because your numerical simulation has a finite particle resolution or a finite cell resolution. So you have a finite smallest length scale imprinted in the problem due to the setup of your numerical simulation. This means inevitably in numerical simulation you will have numerical viscosity, and because this is the case you will have a numerical Reynolds number. And people are supposed to tell you. If people show you pretty pictures, as you often see, then you're supposed to ask, what is your numerical Reynolds number? And this gives rise to big embarrassment and discussions and so on. But if you are ever annoyed by somebody showing you pretty pictures of hydrodynamical flows, ask this question and the discussion will stop. Good. We haven't solved the problem of the creation of magnetic fields. Right? We have a homogeneous equation for the evolution of the magnetic field, and it tells you if you start with 0, you remain with 0. All right, and I told you in the beginning that we can solve this problem only if we take into account that our plasma has two components. At least. We'll have more, but okay. So, generation of magnetic fields. Interesting problem. How do we go about this? Well, let us first write down the equation of motion for the electrons and for the ions. And let us assume for simplicity that the ions are singly charged, so that I can avoid writing lots of sets everywhere. Okay, so I want to start with Euler's equation. I want to start with the density. But now I need to separate the mass densities of the electrons and of the ions. So I'm going to write the density as number density, and I do not distinguish between the number densities of the electrons and the ions because I'm assuming that the ions are singly charged, right? Okay, so this will be the mass density of the electrons. Now I take the total time derivative of the electron velocity. This will be equal to minus the gradient of the pressure in the electron distribution. That could be different from the pressure in the ion distribution. You never know, let's be careful, okay? Then we need to take density times the gravitational potential. This will not separate between the two, right? By the equivalence principle, it cannot. Right? Everything needs to fall in the same way. So we have a single gravitational potential for both of them. All right, now we need a force density. This will be minus n times E, minus because we are now dealing with the electrons, number density to get a force density, and now we have electric field plus V electron over C cross B. That's the Lorentz force density acting on the electrons. Anything else? I think we don't need any other forces, right? Good, that's the equation of motion for the electrons. Now let us simply copy the equation of motion for the ions. Plus Ne, right? Now we have positively charged things. Okay. Now I'm going to divide the first equation by NME and the second by NMI, and then I'm going to subtract the second from the first. All right, I'm going to divide this by NME, then this is gone. I'm dividing this by NMI, then this is gone. I'm going to subtract the second from the first. So then on the left-hand side, I will have the time derivative of the velocity difference between the two. On the right-hand side, I will have minus gradient PE divided by NME plus gradient PI divided by NMI. Sorry, I'm subtracting them. These two terms will be gone. Right? The gravitational force will not distinguish between them. And then I will get E divided by ME times Lorentz force. I'm going to subtract this, so minus E divided by MI, E plus okay. But now look at these different terms. This one is divided by ME. This one is divided by MI. MI is at least a factor of 2,000 larger than ME. So this means that this second term here is of order a factor 2,000 smaller than this term here, if the pressure gradients are similar. Same here, right? So let us now ignore the ion contributions here. Then only the pressure gradient for the electrons counts, and I can drop the E. Okay. Okay, yes. So, this is the equation we are then arriving at. And if we would not do anything else about it, we would get exactly the same induction equation from there. But now we need to add a term that couples the two species. Okay? And I'm going to do this in the following very crude way. I'm adding a friction term. That's so-called Rode Ansatz. Right? The simplest thing you could do if you wanted to couple the two species. Right? So this is not a conclusion from here. This is a conclusion from above, plus an ad hoc friction term to couple the two species to each other. Aha. So now, I want to have a stationary situation. I'm setting the time derivative of the relative velocity to 0. And then I'm going to solve for the electric field. So then I have E over ME times the electric field. I'm bringing this term on the other side. This is minus the gradient of P divided by NME. This is minus E times VE divided by MEC cross B. And this is minus VE minus VI divided by tau. Okay, now of course, you can multiply the whole equation by ME over E and isolate the electric field. And you get as an intermediate step E equals minus gradient P divided by En from here. Then you have minus VE over C cross B from here. And you have ME over E tau VE minus VI. Okay, good. Now we have an electric field. What does this mean? This is an electric field that comes about because, first of all, you would need to compensate the pressure gradient in the electrons with a Lorentz force. And there's a friction term occurring. So you have a balance of 4 forces now. An electric force which balances any difference between the magnetic Lorentz force, the pressure gradient force, and the friction force. Okay. Now, we're aiming at a dynamical equation for the magnetic field. So now we are using a Maxwell equation again. We are going to use the same Maxwell equation again that we have used in the first place to get a dynamical equation for the magnetic field. In other words, I'm now going to take the curl here of the electric field, and I'm going to isolate B dot then. Okay, but before I do this, let me have a look at the total current density. And this will be the current density of the ions, and it will be the current density of the electrons. And because of their different charges, there is a minus sign. So you see that the velocity difference here, VI minus VE, that the velocity difference can be replaced by the current density. All right, now let me collect things over here. and say, all right, if I now take, according to this Maxwell equation, the negative curl of this equation times C, I will get an equation for B dot. Negative curl times C. So negative gives me plus times C. So this gives me plus C over E times the curl of grad P over N. And here you see, if n was constant in space, for example, we would take the curl of a gradient and this term would be gone. But if there is a gradient in n, we might win. We might win because this is now an inhomogeneity in the equation, right? That would survive even if B was 0 in the first place. So this can create a magnetic field. Lovely. Minus C times the curl. So we get plus curl. Now let me write V instead of VE. So we get plus the curl of V cross B. Well, this is a term we had before. That's the advection term. What else? We have minus C times the curl of this. So we have plus CME divided by E tau. Divided by what? E tau. Okay, now here we need VE minus VI. Here we have VI minus VE. So the rest is minus J divided by NE. Yes, so by taking minus C times the curl, we get a plus sign. By taking the different order of the velocities into account, I get a minus sign. So I get this expression here. Sorry, and now I need to take the curl. ME NE squared tau. The curl might act on n, so I need to take this into account here. Then I get the curl of J divided by n. Okay? ME divided by NE. And then I need to take the curl. And I need to multiply with the speed of light. It's like sprinkling over a dish. All right. Now, what do you see? First of all, the first term I would get is the curl of this gradient, which goes away. Next term is the gradient P vector product, the gradient of 1 over the gradient of 1 over n. So this is minus grad P vector product grad n divided by n squared. This is the important term, right? This creates, or this can create a magnetic field. The rest is just as usual. Now we need to see about this one. This is minus CME divided by E squared tau. Curl of J divided by N. That's one term. The next term is minus gradient J. J cross gradient N divided by N squared. But usually currents would be aligned with density gradients. Okay? So this should be going here. Then here, I can use that J is C over 4 pi curl B. Okay. And then this means that I can write B dot is. Look, here you would get the curl of curl B. This would be the usual combination of grad diff B, which is 0, minus Laplacian of B, which is not 0. So we'd get C squared over 4 pi E squared tau ME. Some constants times now plus square B. Here we have our diffusion term back. And what is it caused by? It's caused by friction. Right? This is the time constant for the friction here. And of course, right, if you have non-ideal conductivity, this is because you have friction between the electrons and the ions. Okay, fine. We understand that. Then we have the usual advection term. All right, also fine. And now we have an additional term, minus C over E, grad P, times grad N, divided by N squared. So you see, under the assumption that we have a two-component plasma rather than a single-component plasma, we can derive a new induction equation for the magnetic field, which looks by and large very much the same as it did before. You have a diffusion term, you have an advection term, and so on. But you have an additional term, let's call it the battery term. And this gives rise to creation, or this can give rise to creation of magnetic fields. And if you have a pressure gradient that is not aligned with a density gradient, you will create currents in the plasma. And these currents can give rise to the creation of magnetic fields. There are many more mechanisms how you can create magnetic fields in a plasma. Mostly these are magnetohydrodynamical instabilities. In very many cases, they can be described in a way similar to that one here. Okay. Now, in addition, sorry for the mess that I'm going to create, but now we can use the two different versions of the diffusion term that we now have. This one. And the one that's upstairs. In order to get a model for the conductivity. So, from the version of the induction equation, which is the first on the upper left, on the upper board, you see that the prefactor of the Laplacian of B is C squared over 4 pi sigma. And from our new version of the induction equation, you see that this must be C squared ME divided by 4 pi E squared tau. Okay, and so you get a model for the conductivity. C squared over 4 pi cancels, and you get sigma is E squared tau over ME. All right. Again, you see, if you want to have an ideal plasma, sigma would go to infinity. This means that the friction constant here, the tau, the time scale for the friction to act, would also go to infinity. Then there is no friction. Now you could play a little bit with that and see that this is the classical electron radius times c squared times tau. May make calculating numbers easier, I don't know. Nonetheless. Okay, that's what I wanted to do today. What did we do? First of all, we listed the assumptions that we make if we enter into magnetohydrodynamics. And these assumptions were, you have negligible charge density. You can therefore neglect any electric fields compared to magnetic fields, and we neglect the displacement current compared to the charge current. Then we get a reduced set of 3 Maxwell equations, and together with the Lorentz transform of the electric field, we got one version of the induction equation for the magnetic field. It's the one that you see up there. Second, we looked at the change in Euler's equation that you could get from, or that you will get from the magnetic field. That comes from the magnetic part of the Lorentz force density, and we looked at that. It has 2 components. One tells you that magnetic fields don't want to be compressed. They add to the pressure. They add a magnetic pressure term to the pressure. And there's a second contribution to the force density due to the magnetic field, and that comes from the curvature of the magnetic field lines. And this tells you that, first of all, magnetic fields want to spread out, and they want to be straight. Okay, then we looked at terms that we would have to take into account in the energy conservation equation if we had to. And this gets so complicated so easily that we usually don't do that. I also told you that you can get a set of closed equations from the continuity equation, the Euler equation, the induction equation, and an equation that relates the pressure to the density. Then you do not need the energy equation. Okay, so if we wanted to solve magnetohydrodynamical problems now, we would take the first 2 equations, we would add the continuity equation, we would have to add an equation that relates the pressure to the density, and then off we go, and of course we will do that. Good. Then we looked at the structure of the induction equation compared to the structure of the vorticity equation, so they are exactly the same. They tell you that the change in time of both vorticity and magnetic field is given by a diffusion term and an advection term. And the ratio between the advection term and the diffusion term is called Reynolds number, and that tells you how ideal the flow is, how ideal a hydrodynamical flow is, or how ideal a plasma flow is. And you would call a plasma flow ideal if it has ideal conductivity, that is, infinite conductivity. Okay? And finally, we said our induction equation has a fundamental problem, namely, it does not create any magnetic fields. If you want to create magnetic fields, you need to take into account that typically in a plasma you have at least 2 components, and if you take this into account and derive an induction equation from a combination of these 2 components, then you do find an inhomogeneous term, an inhomogeneity in the induction equation that can give rise to the creation of a magnetic field. So much for today. If you are ever being asked, could you write down the magnetic Euler equation and the induction equation, just don't say no. Good. Then let's meet on Wednesday again. See you.